So here's what I'm kind of thinking of for today. And again, we have 2 more days to cover the rest of chapter 9, so I am in no mood to rush. I feel like there's more time here at the end of the term than I expected. And it might be because time wasn't really an issue last term because all of the lectures were fully online and we didn't have any classes for that last part of the term. So it might be, given a chance to do this class again, it might be that I will slow down the first half of the semester, you know, maybe take another 2 or 3 lectures to do all that, and, you know, eat up some of the time that we're taking here in the latter part of the term. But that being said, if we have plenty of time, I'm going to take advantage of that. Reef poll, nope, not today. We're just doing attendance. I do have a little exercise for you guys later that I'll put up, but we're just taking attendance. So please do register your attendance. That will be 10 out of 10 points for the day. Good. So one thing that I hope I made clear last time is that carbonyl groups in general are good electrophiles. And here we're focusing on aldehydes and ketones. Aldehydes and ketones certainly are good electrophiles, but other carbonyl-containing compounds can be pretty electrophilic too, and we'll learn about that in our last traditional organic chemistry chapter. I'm basically hoping in this class to cover the bare minimum, you know, the most common functional groups so that we get an idea of how they all behave. And besides this chapter on aldehydes and ketones, we also need to do the one, I think, on carboxylic acids and esters. That, I think, is enough. That will cover the major functional groups and give you a sense of how they all behave. But carbonyl groups in general are good electrophiles, and the reason for that is twofold. First of all, we understand that the carbonyl group, the carbon-oxygen bond, is highly polarized towards the oxygen. Right? You could also write this, by the way, your Gen Chem professor might have written delta plus by the carbon, delta minus by the oxygen. You can do that too. It means the same thing. You can write it either way. Or you can show this little polarity arrow. I'm kind of a polarity arrow guy. The reason I like this is you put this little cross in the tail of the arrow and it looks like a little plus sign. So it's a nice reminder. But if you'd rather write this as delta plus by the carbon, delta minus by the oxygen, to show that the carbon is a partial plus charge and the oxygen a partial minus charge, due to the oxygen winning the tug of war for electron density by virtue of being so much more electronegative than carbon, you can do it either way. I don't care. I have no preference. But that's one reason. Because the oxygen is sucking away electron density from the carbon, it has a partial plus charge on it. And so no wonder that nucleophiles are going to want to attack that carbon. And we'll look at a couple of such nucleophiles today. We're certainly not going to look at all of them. I mean, I'll leave a couple more of the more important ones for class on Monday, because they're ones that we'll need, I think, in order to understand carbohydrates better. But we're certainly by no means, I'm certainly not going to make you guys responsible for all of them. You know, there are some that just we wouldn't really run into quite so readily in living systems anyway. So we'll stick to the more important ones. The other reason that carbonyls are such good electrophiles is because they're resonance stabilized species. There's another resonance form where with just a single bond between the carbon and oxygen and a minus charge in carbon and a minus charge in oxygen and a plus charge in carbon. And this certainly is a minor contributor to the overall molecular orbital picture. Depending on what the groups are that are bonded to carbon, it's probably going to be, any given molecule is probably going to be described maybe 98%, if not more, of this structure, and maybe only 2% this way. And again, remember, it's not an equilibrium. It's not flipping back and forth. There's one true structure that is at all times a hybrid, a mixture of those two structures. But the fact that the structure has even a small component of this, again, just lends credence to the idea that this carbon has a partial plus charge on it. No wonder we can expect nucleophiles to attack it. And that's what we're going to see consistently in the reactions that we look at. The ones I'm hoping to look at today, first of all fall under the category of nucleophilic acyl addition reactions. And they fall roughly into this type of category, We'll start with an aldehyde or ketone, and we'll treat it with some nucleophile. For us today, this is going to be either water or hydroxide ion, depending on whether we're looking at it in acidic or basic medium. And the other one we're going to look at is cyanide ion. Yes, that's cyanide ion. And in the end, you get an addition product, which will look something like this. Normally, we use a protic solvent with this type of reaction. Today, for us, that's going to be water, for sure. Next time, we're going to look at, I believe, what will happen if the solvent is an alcohol. And we'll talk about the formation of hemiacetals and acetals. And that's not going to be, will not only be relevant for carbohydrates, as I said, but it also points back to nucleic acids, where we said you got this NO-acetal, which is a similar type of species. And so we'll learn how all that works on Monday. I am going to get a little bit into mechanisms today. I hesitate to give you guys too much of that. I just don't want to burden you overly with mechanisms. But I think today is a good day to do it, because the reactions we're going to look at today have relatively simple mechanisms, 2 or at most 3 steps. Learning the mechanism for acetal formation, that would be outrageous. The thing's got like 8 or 9 steps. And I just don't see any value to you guys in learning that. But the reactions we're going to talk about today, I think, are valuable. They'll give you an idea of, first of all, that a reaction can happen in acidic medium or alkaline medium, and that's going to have implications for how the mechanism goes, for sure. Then also, it gives us an idea of what species do we invoke when we're an acidic solution? What if we're an alkaline solution? And it's somewhat different, but I think with relatively simple reactions like the ones we'll do today, I don't think it's going to be overly burdensome. So I'll try to lead us all through that. And I think with that, we might as well, I'm in section 9.8 right now, if you're following along, by the way. All of the reactions we're going to look at today and a few on Monday as well fall into this category of nucleophilic acyl addition. And I think you can see that now that we've given the definitions of all 3 of those words, I think you can see that this makes sense. Remember, an addition reaction is when 2 or more things come together to make one big one. And that's exactly what's happening here. So this carbonyl compound plus this nucleophile come together to make one species. And again, it will pick up the proton from the solvent one way or the other. So substituted alcohols of this type are very common types of products for reactions of, again, a wide variety of nucleophiles. We'll just look at some of them. You know, we're certainly by no means going to do all of them. But there's a large variety of nucleophiles that can react, and again, not just with ketones and aldehydes, though that's what we're focusing on in this chapter, but there also are reactions of this type with other types of carbonyl compounds as well. And then later on in chapter 10, I believe, we'll also discuss a type of substitution reaction that these carbonyl compounds can undergo. But like I said, that comes later. But all of this involves nucleophiles reacting with the carbonyl carbon, and all of that is because that carbon is electrophilic. It's got a partial plus charge. So if so far you've got that the carbon atom in any carbonyl group, in any carbonyl-containing molecule is a partial plus charge, you're good. You're following along well. If you've got that, we're doing well. And so what I'd like to start with then today, I'd like to cover at least 2 reactions that can occur with aldehydes and ketones. One of them, I will admit, and I admitted as much in your class notes, is actually not useful synthetically. In fact, if anything, it's the opposite. It's normally the sort of thing that we try to avoid happening. But I'm going to go over it anyway. We cover it, by the way, in Chemistry 228 also. But I'm going to go over it anyway because it's a nice model for other types of reactions. And that is the reaction of aldehydes and ketones with water. And well, the way this works is any aldehyde or ketone so I'm just going to use R1 and R2 here. And we're just going to say this is an aldehyde or ketone. And we'll get to some actual examples. But any aldehyde or ketone can react with water under either acidic conditions or alkaline conditions. Under acidic conditions, what you'll see is that we treat this with dilute acid, dilute aqueous acid, which we generally write H3O+. And maybe I'll put over here to the side, it's important to be aware that H3O+, if you see it given or listed as a reagent, it implies H2O is also present. What it means is that you've got a dilute solution of aqueous acid. And you could get that by dissolving a small amount of any, pick your favorite inorganic mineral acid, a little bit of sulfuric acid, or maybe HCl, or phosphoric acid would also work, but any decently strong inorganic acid in a small amount. So we're using, again, a dilute solution of acid. But whenever you see H3O+, H2O is also there. And now that being said, sometimes in OWL you'll notice they write H3O+, comma, H2O. And maybe I'm splitting hairs here, but I just have to tell you, I'm not a fan of that. To me, that looks redundant, because if you say that we've got H3O+, you can't have a bottle of H3O+ ions. It's just not possible. What it means is that you have a dilute aqueous acid solution. So if you ever see H3O+, and certainly you can take it this way in my exams, but if ever you see H3O+ mentioned, that implies that H2O is also there. You have to have water around to have hydronium ions. That's how I think about it. Again, maybe I'm being overly picky, but do take note of that in case you do see that on OWL. Maybe you can say to yourself, okay, there's this thing, it's questionable. I don't like doing it. I think it's redundant. So you can use acidic solution, or this will also happen in an alkaline solution. And what would the equivalent alkaline solution look like? Well, it would mean that you have hydroxide ion dissolved to some degree in water. So either of those sets of conditions will work, and either of them will give you the so-called hydrate of the aldehyde or ketone. And that will look something like this. It will have two OH groups. We'll still have R1 and R2, and another OH group down here. We call this an aldehyde or ketone hydrate. That's usually what that's called. And so basically, of these two OH groups that you see here, one of them came from the reaction solution, either aqueous acid or aqueous base, and the other oxygen is the one that was in the carbonyl to begin with. So you'll notice we go from a carbon-oxygen double bond to a carbon-oxygen single bond. And again, I think you'll see this reaction is exactly of this type that we talked about up here. It's an example of a nucleophilic acyl addition reaction. And the reason that I say this is, if anything, the opposite of useful is because normally we don't like having these hydrates around. If we're keeping a sample of some aldehyde or ketone around, and we want to be able to use that later, well, we don't want to build up any considerable amount of this hydrate. We want to keep water from reacting with this, because whereas this compound will be reactive for whatever thing we wanted to use it for, this compound will not be. That one's dead. So it's not rare, especially in applications where you want to be sure that you keep your aldehyde or ketone, whether it's acetone or 2-butanone or some aldehyde, if you want to be sure that you keep it scrupulously dry, it's not rare to store it over some drying agent. And again, those of you who were in lab might have used some drying agents already. Magnesium sulfate or sodium sulfate or calcium chloride are very common ones. And these things will soak up any water before this can happen. Now, I really should almost have drawn two arrows here. I should have drawn like an equilibrium arrow. So this now is not resonance. This really is an equilibrium. These really are flipping back and forth. But under normal conditions, we really want to do what we can to be sure that the equilibrium lies to the left, that we're favoring the carbonyl compound not turning into the hydrate. Because again, these things, first of all, there's really very little, if anything, you can do with them. And so they're just not synthetically useful. There's little to nothing that you can do with these. In terms of using them for synthesis, it's pretty dead. They're unreactive. This guy is fine. That one, not so much. But the reason, again, that I'm talking about this reaction is that looking at both of these mechanisms, both the one in acidic medium and the one in alkaline medium, I think is very illustrative in understanding a pretty important part of organic chemistry and how organic molecules behave. And like I said, I don't normally want to burden you with a lot of mechanism. This is certainly something that I don't expect to be, 40 points on the next exam. There might be a little bit on it, but I'm doing it here purposely because these mechanisms are relatively short, 2 or at most 3 steps. I certainly would never expect you guys to learn one of these monster mechanisms that is 6, 7, 8, 9, 10 steps. I just don't see how that would do you any good. But 2 or 3, that's fine. I think we can handle that. And I think it will be useful. So just as an example, let's see here. My usual manner, I think I have enough space. So let's look at a particular example. No, I'm sorry, I'm nervous. I think I need more space. Let's look at a particular example. Let's take acetophenone, just because it comes to mind. Is it okay if I do pH for a benzene ring, C6H5? pH for phenyl? You can write that too if you like, or where I've written pH, if you want to write C6H5, perfectly acceptable. Everyone will understand that. Or if you don't like any of the above and you want to just draw out the benzene ring, also fine. Perfectly fine. Do whatever works best for you. But let's say that we start with acetophenone, and let's consider the mechanism in acid first. This is actually a little bit more difficult, because this is the one with 3 steps rather than just 2. In the end, we can expect to get the hydrate, which will have 2 OHs. And again, we're not showing, actually that carbon isn't even chiral, so it doesn't even matter. But I'm not indicating any kind of stereochemical issue here at all. You can put the phenyl group and the methyl group and the 2 OHs anywhere you want on those 4 bonds. We're just drawing a flat structure here. Not, as I said, not that even that matters, because this carbon's not chiral, right? Because there's 2 of the same group, so game over, not chiral. But that's the product we can expect to get. So what would the mechanism look like? And again, by mechanism, we mean that we're going to draw curved arrows to show step by step how this molecule turns into that molecule. And it will do so in 3 steps. The first step, did you say it doesn't matter whether we draw? Well, no, the CH3 or phenyl in these 2 OHs. Put them on any of the 4 bonds you like. It's the same thing. Right? I say that because I think I put the OH down here in the other one. It doesn't matter. It's the same thing. And the way you know that is because it's just an sp3 hybridized carbon, and there's no stereochemical issue. I know that this carbon's not chiral because it is 2 of the same group on it. So it doesn't matter. If you want to put the OH down here and the CH3 over here, it's fine. Or any other variation on that is fine. It's the same thing. So in the first step, at least I hope that helps. In the first step, what we need to do is put a proton on that oxygen. And that's real common for reactions in acidic medium. Because if we don't, if we just say bombs away and have our nucleophile attack that carbon, that's going to put a minus charge in that oxygen. And that doesn't make sense since we're in an acidic medium. And so this is one of the main principles I wanted to get across today. You want to be sure when you draw your mechanisms that all of your structures make sense given what the reaction medium looks like. Here we're in an acidic medium. It doesn't make sense to show any strongly basic anions like OH minus or NH2 minus or an oxygen with a minus charge here. That doesn't make sense. You can't have that in an acidic medium. those species can't survive. They would be immediately protonated. And so the way I generally tell students is, in acidic medium, I don't want to see any anions, the only exceptions being the conjugate bases of very strong acids. So things like Cl-, Br-, HSO4-, the conjugate base of sulfuric acid. Those are fine in acidic medium, but no alkoxides, no hydroxide, no nitrogens with a minus charge, certainly no carbanions. Those don't make sense in an acidic medium. They couldn't exist there. They would be immediately protonated. So that's why we need to protonate that oxygen. And so let's review then what we have in the solution. We've got this stuff, we've got H3O plus ions, and we've got water, which again is implied by H3O plus being there. And that's it. Those are the only things we can use. So we have to think, what are we going to use to put the proton in the oxygen? Well, which is a better acid, H3O plus or water? Not a trick question. I think you know the answer. Of course, the hydronium ion's a better acid. So that's what we'll use. There's your H3O plus. And so remember that arrows always and only are used for movement of electrons, not for atoms. But not for movement of atoms, not for movement of charges. So you don't use an arrow to say this H goes here. No, that's not how this works. Rather, we need to think of this as one of the lone pairs, and it doesn't matter. I could have done it on the other side also. But one of the lone pairs on the oxygen is going to reach out and grab H plus off of the hydronium ion. And again, any reasonable variation of this is fine. I drew this arrow kind of curving up. If yours curved down, that's fine, as long as the arrow starts and ends in the right place. Now, of course, we can't have just this arrow. Otherwise, hydrogen's going to have 2 bonds, and that's no good. Hydrogen wants to have only 1 bond. So we need to show that this hydrogen-oxygen bond breaks. And so those electrons in that bond are going to go onto the oxygen atom and get rid of the plus charge in oxygen, because now instead of 3 bonds in 1 lone pair, the oxygen will have 2 bonds in 2 lone pairs, so it'll have a formal charge of 0. And this is just going to make a water molecule. Often we don't even draw that, because there's already plenty of water around. And we're interested in the organic portion. But what we do get after that step is the acetophenone protonated. No, I don't like that. Let me make that a little clearer. I mean, I almost drew it without the OH bond. You don't really need to draw the bond, but I just want to be sure that I'm being clear. And so that's the intermediate that you'll get. Now that makes sense in an acidic medium. Cations are okay. Oxygens with a plus charge, just like H3O plus. Things like that are fine in an acidic medium. Strongly basic anions, no way, doesn't make sense. So we get this intermediate, and now this is going to be what our nucleophile will attack. And now we don't have to worry about our nucleophile attacking this carbon, because now we won't get an oxygen with a minus charge, now that we've protonated that oxygen beforehand. So I don't know how many more of these we're going to see. I don't think we're going to look at very many of these mechanisms in detail, but it's pretty common if you're looking at a reaction in acidic medium of a carbonyl compound, almost always you'll see we protonate that oxygen first before we do anything else. So now we just need to figure, what is our nucleophile going to be? Well, again, let's look at what we've got. That's another really important principle. If you could ask my 227 and 228 students, they'll tell you I say this all the time. You need to look at what you're given when it comes to writing mechanisms. You can't just pull something out of thin air that's not there and use it in your mechanism. You can only use species in your mechanism that make sense with what you're given. And again, what I'm given is this compound, some H3O plus ions, and water. That's it. So what's the most nucleophilic species there? I think you'll agree with me, it's water. Water is nucleophilic, H3O plus is not. That's an acidic species. If anything, that's a Lewis acid, not a Lewis base. So water is the most nucleophilic species we've got. So that's what we need to use. as our nucleophile. And that is going to attack our carbon. And any arrow at all like that, you just want it to start and end in the right place. It doesn't have to look exactly like that. You just want to express that one of these lone pairs in oxygen is getting donated towards that carbon, at which point we better break a bond on that carbon, or a carbon will have 10 electrons around it, and that's not allowed. So of course it will do is we'll break the carbon-oxygen pi bond, and we'll put those 2 electrons in the pi bond onto this oxygen, which will have the added bonus of getting rid of the plus charge in this oxygen. I'm sort of running out of room here, so I'm going to go like this. And that will give us another intermediate. We are almost done, but not quite. Now I guess I felt like drawing this other oxygen down here, where I drew it up here before. It doesn't matter. It's the same thing. So we're almost done. We're almost at the product. We just need to pull one of these protons off, which will get rid of the plus charge. And so now we need to ask, what is around to use as a base? And again, all I have is besides my organic starting material is H3O plus and H2O. Well, H3O plus is many things, but a base is not one of them. So water is not the greatest base in the world, but in this case, it's good enough. In fact, in this case, it's all we've got that can act as a base. The reason I'm stressing this is that both for this step and for this one up here, what I've noticed, at least my 227 students struggle with the most, is they really want to use OH minus here to be the nucleophile. And they fail to see that that makes no sense. You can't have OH minus ions in an acidic medium, not in any reasonable concentration. Okay, maybe at 10 to the minus 25th molar or something like that, but certainly not in any concentration did it make any sense at all to use that in a mechanism in an acidic medium. In alkaline medium, now we're fine using species like OH minus, but not an acidic medium. We can't use any strongly basic anions. Those can't live in an acidic medium. So you got to draw species that make sense. So the only thing that can act as a base is the water molecule, and that will pull off one of those 2 protons. It doesn't matter which, they're the same. Then we break the hydrogen-oxygen bond, we put those electrons onto this oxygen, which gives us back our neutral oxygen atom, and that's the product. And with that, we're done. So it's 3 steps. We start by protonating the carbonyl oxygen. Then the water attacks, that's our nucleophile. And then we get a protonated species that we just pull off the proton and we're done. So 2 proton transfers surrounding a nucleophilic addition. So it's just 3 steps. So that's the sort of mechanism that we see for a reaction of this type that's an acidic medium. And we'll contrast this in just a moment with what that looks like in alkaline medium. And I think you'll find, at least this is always my opinion. This is my opinion on the matter. It's what I've always seemed to notice. Whenever you have 2 similar mechanisms, one in acidic medium and one in alkaline medium that are otherwise the same, to me, the one in alkaline medium is always easier. There's fewer steps and it's more straightforward. In fact, in this case, I think we'll find it is just 2 steps as opposed to 3. So you may disagree with me, but that's how it seems to me in cases like this where there's an acidic and an alkaline version. Good, so what else do I need to say about that? Oh, another thing I'll point out, one thing you'll notice about this reaction is that it's acid catalyzed. Ooh, now how did I know that? Do we have homework due tonight? Well, it couldn't be this chapter, since we're not going to be done with it. Yeah. And again, a lot of these last OWL assignments, a lot of them you'll see they're not graded. I still suggest you do them, but if they gave me only 3 questions in the mastery. I don't want to grade that. I don't think that's right. I don't think that's fair to you. Good, so this reaction is acid catalyzed. Why? Or before we get to why, what does that mean? Well, it means that the acid is not consumed, right? It only speeds up the reaction. And if that's to be true, then we'd better make sure that no H pluses are consumed by the reaction. And I think you'll see that's the case. Here, I'm taking an H plus in order to protonate this oxygen. So I owe you an H plus back. Now my water attacks, there's no proton transfers here. We get this intermediate, but lo and behold, in this step, I'm paying you back. I'm giving you the proton back to regenerate the H3O plus. So actually, in principle, this should work with just a little tiny speck of acid with a very dilute aqueous acid solution. So this is actually acid catalyzed. The base version is not going to be catalyzed. That's going to be base induced. That will actually use up a mole equivalent of hydroxide ion. I think you'll see that in just a moment. So like I said, I got the one that's more difficult out of the way first. I think you'll see the base version of this gives the same product, but is only 2 steps instead of 3. Good. Any questions on the acidic medium mechanism? And best way to learn this, by the way, make up your own aldehyde or ketone. Replace the phenyl group with something else, replace the methyl group with something else. Maybe put a long alkyl chain on one side and maybe a hydrogen on the other. So practice seeing what that looks like with an aldehyde. Figure out what the product looks like and practice working through those steps. And again, like I said, your mechanism does not have to look exactly like mine in order to be correct. Not to mention, of course, your remaining exams are still going to be multiple choice, so you won't be graded directly on your mechanism drawing, but it still is worthwhile practicing it. And I'm just being real with you. That's what I did when I was in college. I just made up my own molecules and drew out the mechanism again and again and again. It seemed to work pretty well for me. So it's certainly the best method I can recommend to you guys in terms of learning this information. But this, for us, I think is as bad as it gets in terms of mechanisms. I don't want to do anything more complicated than that. And I think you'll notice looking back, I've skipped most of the mechanisms because a lot of them are very, very multi-step. This one's not too bad, but I don't really want to push it beyond that. Good, so we're okay on acid catalyzed addition of water to aldehydes and ketones. Let's see. Well, let's look at the same thing then in alkaline solution. The product will be the same, but the mechanism will be different. I'm still seeing clicking going on up here. That's good. Please make sure you register your attendance. Now, I should mention, this could say H2O and OH minus, but be prepared, instead of saying OH minus, they might say NaOH or KOH. Well, those are the same thing, right? Those are ionic species, and the alkali metal ion, the Na plus or the K plus, is just a spectator ion. It doesn't do anything, doesn't participate in the chemistry. So just so you're aware, you might be given that as well, NaOH or KOH, and it means the same thing. And you'll see we don't even use the alkali metal ions in the mechanism, but the product will be the same. It will be the hydrate of acetophenone. Again, you'll have 2 OH groups as well as the phenyl and methyl groups that we started with. And you can attach those 4 groups to the carbon in any order. It doesn't matter. That carbon's not chiral, so there's no stereochemical issue. Good. Well, and the difference is now we're in alkaline solution. So now we turn the rules in their head. In acidic medium, we said we didn't want to see any anions, certainly not any strongly basic anions. No OH minus, no alkoxides, no oxygens or nitrogens with a minus charge, certainly no carbons with a minus charge. Those don't make any sense in acidic medium. Now we're in alkaline medium. So now the rule is going to be turned on its head. Now, in alkaline medium, I don't want to see any cations, with the possible exception of metal cations, Na+, K+, Ca2+. Those can live in an alkaline medium. Not that they even matter, because they're not ever going to get used in the mechanism. But I certainly don't want to see any oxygens with a plus charge, no carbons with a plus charge, nothing like that. Those species don't make sense in an alkaline solution. They couldn't survive. They would immediately get deprotonated or otherwise decompose to form something more stable. But you're not going to be able to support a plus charge in alkaline solution, except, as I said, in a metal cation, which those are going to be spectator ions anyway. So what that means in terms of our mechanism, like I said, to me, it always looks simpler and more straightforward in alkaline medium than in acidic medium. And so, whereas we had to protonate the oxygen first in alkaline medium, here we'd better not protonate that oxygen, because then we'd have an oxygen with a plus charge, and that's no good, not in alkaline medium. Acidic medium, it's fine. Alkaline medium, no way. No species like that could survive an alkaline solution. So even though we certainly couldn't do this in acidic medium, in alkaline medium, bombs away. Our nucleophile just attacks that carbonyl carbon directly. And how do we figure out what our nucleophile is? Well, again, always look back at what you're given. That's maybe another thing you can take from today's lecture, that if you remember that, we're in good shape. When in doubt, when it comes to figuring out what happens in a reaction, go back and look at what you're given. And if it's something that you need to write out a mechanism like this, there'll be some like that on OWL too. Oh, fair warning, mechanism drawing on OWL is a bit of a pain. You kind of have to get your mouse pointer on exactly the right square tenth of a millimeter, or it'll count it wrong. So admittedly, it's a little bit frustrating at times. But be that as it may, go back and look at what you're given. All I have besides my organic compound is water and hydroxide, well, and whatever the counter ion is, which again is not going to do anything. It's just going to balance out the minus charge of an anion. So I think you'll agree, of these two species, definitely hydroxide is more nucleophilic than water. We said that earlier in chapter 6, that other things being equal, an anion will be more nucleophilic than a neutral compound. And here other things are equal. We're comparing two otherwise identical species. They both involve oxygen. So bombs away. Our nucleophile goes right ahead and attacks that carbonyl carbon. And we break the carbon-oxygen pi bond just like before, and we wind up with a minus charge on that oxygen, which is perfectly fine since we're in alkaline medium. Acidic medium, that'd be no good, but alkaline medium, we are good to go. So minus charge on that oxygen. OH over here. And you get this intermediate with a minus charge in oxygen. And again, since we're in alkaline medium, we're fine. There you can have anions. Certainly oxygen with a minus charge. And so now all we need to do is put a proton in this oxygen and we're done. We get the final compound we expect. So how do I know what to use to put the proton on? H3O plus? Well, not so much. There is none here. We're in alkaline medium, so there's not going to be any H3O plus ions. So our choices of what to use to put the proton on are water and hydroxide. That's all we have besides our organic compound. And I think you'll agree, water is a much better acid than hydroxide ion. Because when you pull a proton off of water, you get hydroxide. And there's already some of that around. So, and I could have drawn this on the other side of the molecule also. But to show water protonating that oxygen, we'll just have our lone pair on that oxygen, any one of those three lone pairs, it doesn't matter which, they're all the same. And that's going to pick the proton off of our water molecule. We'll break the hydrogen-oxygen bond, and we'll put the electrons onto this oxygen atom. And so it'll make an OH minus ion. Often we don't even draw those inorganic species. Actually, I can be really lazy. There we go. So that gives us the product directly. So only two steps. in alkaline solution. The nucleophile just attacks, and then we pull a proton off of water. And now I think you'll see why this is not base catalyzed. This is actually going to consume one OH ion, one hydroxide ion for every molecule of the organic starting material. So I would not call this base catalyzed. You'd want to call this base induced or something like that, maybe. But other than that, that's it. So where are we at now? 3:40. Oh crap, that means I have 5 minutes. Drat. I mean, I'm not worried because we still have loads of time to complete the material. Means I might need to save cyanohydrins for next time. But yeah, I think that's otherwise a good place to stop. We can save cyanohydrins for next time. We'll be fine. Good. So that's our little introduction into mechanisms in acidic and alkaline medium. All right, that says 344. Well, I'll just show you this is how I did it. I just added in all the arrows. I think you'll see that looks just like what we did with the other example. I will say that I'm somewhat limited in how I can draw mechanisms on ChemDraw. I can't always make the arrows look quite as beautiful and curvaceous as I want them to look, maybe. I can't, make them quite as subtle as I want. But I would say, to me, those arrows are acceptable. They at least all start and end in the right place. So although that is already on eCampus, I do want to go in and fix that one thing, and then I'll re-upload it. Other than that, I am out of time. So I will see you all on Monday. Have a good weekend.